Dear students, in this lecture, we will discuss two kinds of chromatography techniques, gas chromatography and high performance or high pressure liquid chromatography. So let us start with gas chromatography. So this diagram is a representation of the gas chromatography equipment or how a gas chromatography works. So gas chromatography, from the name itself, it's clear that the mobile phase is a gas. So the gaseous mobile phase or the gas will carry your components or your mixture inside a column, and the separation of your components taking place in the column, and you will get the chromatogram. So starting from here, we can see a cylinder which contains the mobile phase gas. We call it as a carrier gas. So normally this carrier gas should be inert, like nitrogen, argon, helium kind of inert gases. So this gas, we adjust the pressure of this gas by using some pressure regulators, and you can also adjust the flow of gas, how much volume of gas should pass through the column. Okay, so here you can see this is a column oven. So that means your column is inside an oven. So the reason is, when a gas chromatographic separation is taking place, normally the column is in a higher temperature, so you can control the temperature of the column by using temperature regulators. So it depends on the kind of components which you are going to separate. You can program all these things. Okay, so here is your injection port. So that means your mixture is injected somewhere here. So your mixture should be dissolved in a suitable solvent, and that solvent should be of low boiling point, so that when you inject in this column, which is in a particular higher temperature, your solution, that means your mixture which is dissolved in a solvent, that will evaporate to gaseous state, and the carrier gas which comes from here, that will carry your mixture through this column. So inside the column, the separation of the components take place, and different components reach in the detector at a different time, so that you will get a gas chromatogram where in the x-axis you will get a retention time and you will get different peaks. So depending on the how many number of peaks you got, you will know, you will get the idea how many compounds present in your mixture. Okay, so that's how the gas chromatograph works. So gas chromatography can be of two types, gas liquid chromatography and gas solid chromatography. However, gas liquid chromatography is more important. So mobile phase is definitely a gas. So the stationary phase is solid in a gas solid chromatography and liquid in a gas liquid chromatography. So we are discussing about the gas liquid chromatography. So in a gas liquid chromatography, the stationary phase is a non-volatile liquid. So the stationary phase is a liquid that should be non-volatile, because you are keeping your column in a higher temperature, and suppose your stationary phase is volatile or its boiling point is very low, your stationary phase will evaporate. So the stationary phase liquid should be non-volatile, and that is immobilized on a solid support. For example, methyl silicon or polyethylene glycol. These are non-volatile liquids. You can support or you can coat this liquid on appropriate inert solid support. Okay, so there are two kinds of column. One is packed column and the second one is open tubular column. So packed column is around 1 to 10 meters long and 2 to 6 millimeter in a diameter, which contains small particles of porous diatomaceous earth, Kieselguhr, which is a spongy siliceous material. So that is packed in the column. Whereas in open tubular column, so your liquid phase is coated on a capillary wall of chemically modified glass or fused silica. So the column normally has a length of 15 to 100 meter and internal diameter of 0.1 to 0.53 millimeter. Okay. So the mobile phase, as I already mentioned, it's a gas, and you can also call that as carrier gas, which should be pure and chemically inert, so that your carrier gas won't react with the components in your mixture. So normally we use helium, argon, nitrogen, these kind of inert gases that we use as mobile phase or carrier gas in gas chromatography. And the principle of separation, so already learned that, because here your mobile phase is a gas, and in this particular case your stationary phase is a liquid. So it's a gas liquid system, so that the principle is partition. So different partitioning of the components of a sample in the vapor state between the mobile gas phase and the stationary liquid phase. So that is the principle of separation. So the detectors what we use normally are thermal conductivity detector, TCD, or flame ionization detector. We have a gas chromatograph in our college which uses flame ionization detector. So flame ionization detector means in the detector your components, when your components reaches in the detector, that will combust with the flame present there. So for that we use hydrogen gas in the flame ionization detector, and we also need oxygen for the combustion. So now the gas chromatograph in our college contains 3 cylinders. One is for the carrier gas, which is helium, argon or nitrogen. The other one is for hydrogen, and the third one is for air or oxygen. So hydrogen and air is for the flame ionization detector. Okay, so these are the detectors used, common detectors used in gas chromatography. Now, so for any chromatography technique, the result what you got is called the chromatogram. So in a gas chromatography, the result what you obtain from the computer is called gas chromatogram. So in a gas chromatogram, you have an x-axis and you have an y-axis. Okay, so your x-axis is the retention time, means the time taken by each component to reach the detector, and y-axis is relative abundance, how much amount your compound present in your mixture. Okay, so here this figure represents the result of a gas chromatography conducted in pesticides. Okay, so in this gas chromatogram they are identified 20 different peaks starting from 1 here to 20. There are a couple of peaks which comes before that, so that could be either peak of your carrier gas and the solvent which you used to dissolve your mixture. Okay, so we neglect those peaks, so they identified 20 different peaks. So that means this mixture contains 20 compounds, 20 components. Initially when they injected the sample, that contains 20 components. Okay, so when this mixture reached in the column, it started to separate the components, and these components reached the detector at a different time, and you can get the time for each component looking at the x-axis. Okay, so they have identified the 20 components. They have given the name of each component here, which is not of your interest. So this is a gas chromatogram. So gas chromatogram is basically a graph where retention time is plotted on the x-axis and the abundance on the y-axis. So from a gas chromatogram, you will get an idea how many components are present in your mixture by counting the number of peaks obtained and subtracting the peak of your solvent and peak of your carrier gas. So the rest give you how many components are present in your mixture. So that is one idea you can get by analyzing a gas chromatograph. There is one more point which is very important. So the area under each peak is different. So why the area is different? The area is proportional to the amount of component present in your mixture. So the peak has highest area. That means the component corresponds to that peak is present in large amount. Okay, so that's very important, because by analyzing a gas chromatogram, you can also get an idea about the concentration of your component in the mixture. Okay, so here I have given a diagrammatic sketch of a chromatogram, and just focuses two peaks, peak A and peak B. So you can determine the area under each peak. So normally the instrument will determine by itself. You can also determine manually. So how the peak area is determining, if you look at here, area peak B means the area under this peak is calculated by measuring the height of this peak. Okay, so they mentioned that comes 122 millimeter, and the width of this peak. But when you measure the width of this peak, you know that the width is different from the bottom to top. So from where you will measure the width, for that you have to take the half of the peak, so half of the peak height. So this is the area where you have to take the width of the peak. So that is measured here is 19 millimeter. Okay, so you multiply the height and the width measured at the half the way of the height of the peak. That will give you the area of peak B, which is calculated here is 2320 millimeter square. Similarly, you measure the area of peak A in the same fashion. So the height is 40 millimeter and the width at half distance of the peak is 17 millimeter. So the area calculated will be 680 millimeter square. So the total area, which is constituted by these two peaks, is the sum of this, which is 3000 millimeter square. Okay, so the total area by the all components present in this mixture is 3000 millimeter square. So now you can determine the concentration of each component. For example, if you take component A, its percentage, peak area percentage is, here it's 680 divided by total area 3000 into 100, that is 22.7 percentage. And for B, component B, that is 2320 divided by 3000 into 100, that will give you 77.3 percentage. So this particular mixture contain two components, and component A has a concentration of 22.7% and component B, the rest is component B, which is 77.3%. So this mixture contains more B than A. And you can also determine the ratio between B and A, which is 3.35. So that means 1:3.35. So your mixture contains component A and B in the ratio 1:3 approximately. So that means by analyzing a gas chromatogram, you will get an idea about how many components are present in your mixture. Also, you will get an approximate idea how much amount of each component present in your mixture. Okay. So, which is explained here in sentence. So, number of peaks correlates number of components in sample. Area under each peak correlates the relative concentration of that component in the sample. The retention time under different conditions can be used to identify each component. So that is another important thing. That means your components in your mixture that reaches the detector at a different time. So that is the retention time for each component. So if you conduct the gas chromatography for the same mixture under similar conditions means the carrier gas should be the same, the pressure of the carrier gas should be the same, the flow rate of the carrier gas should be the same. You have to dissolve your mixture in the same solvent, and you have to keep the column temperature the same. So if you keep every conditions of the analysis same, then a component will give the same retention time wherever you conduct this experiment. So that is very important about the retention time. So the retention time is something like a characteristic property of a particular component. So you can also get what is present in your mixture. If you have a library for different components with retention time, and if you conduct the experiment the similar conditions as in the library, then you can say that okay, by looking at the retention time, this peak corresponds to this compound, this peak corresponds to this compound. So my point is, gas chromatography can be used as a quantitative as well as qualitative analysis technique especially for the organic compounds. So area under a peak is the peak area multiplied by the peak width at half height of the peak. Then percentage of component is obtained by area under the component peak divided by total area multiplied by 100 will give you the percentage of your component. Okay. Now let's see what are the common applications of gas chromatography. So it can be used for the separation of complex organic and biochemical systems, qualitative and quantitative analysis, as I mentioned, of organic mixtures, impurity checking of organic compounds. Very important application is you can couple this gas chromatography with other techniques such as mass spectrometry or IR spectroscopy or NMR spectroscopy. So what is the advantage of that? The advantage is, suppose if you have a mixture, you don't know how many components are present in your mixture. Also, you don't know what are these components. Okay. So what you will do is, you will conduct a gas chromatography for this mixture so that in the column your components get separated. Okay. So when it reaches the detector, they reach in different time. Okay. So you connect your outlet of gas chromatograph to any of these instrument. For example, if you connect the outlet of a gas chromatograph to a NMR instrument, so what will happen is, each component will go to NMR and you will get the NMR spectrum of each component. So that means if you have an NMR spectrum, you can almost 100% surety you can predict the structure of your component. So for a complete analysis of a compound, this the gas chromatography coupled with the NMR spectroscopy is useful. Also, if you couple your gas chromatography with mass spectrometry, that is very common, what we call the GCMS. So if you have a GCMS, gas chromatography will separate the components in a mixture, and the mass spectrometry or mass spectrometer that will analyze the fragmentation pattern of your component, so that you will get an idea of what exactly is the component present in your mixture. Okay, so this is the one of the most important applications of gas chromatography. You can also analyze gaseous samples in gas chromatography. So gas chromatography, especially when it coupled with the other analysis techniques, is one of the mostly used analytic technique in chemical sciences and other scientific areas. Okay, so thanks for listening to this lecture.